Hi everybody! In this video, we'll learn about precipitation. Our first experiment is this copper sulfate. In this copper sulfate, after I put in this iron nail, the copper will become a solid and the iron will float away into an ion. So, let's get this iron nail and then plop it in. And tomorrow, let's see what happens to the iron nail. See you tomorrow.
Hi guys.
Welcome back. Now, this is actually the copper sulfate I actually prepared yesterday. Now, these little powders are actually copper actually shaked off. And this solution is now yellow, which means that the iron floated away into the solution. In other words, this is no longer copper sulfate, but is now iron sulfate. Now, let's see another alternative of precipitation. This yellow thing is a test tube full of saturated ammonium iron sulfate. So, he's gonna pour in the sodium carbonate solution. Wait, whenever I say stop. Okay. The solution is becoming a little darker, right? That's because the sodium carbonate will precipitate the iron out of the solution, while the sodium from the sodium carbonate
It's kind of like an orange juice.
Except it contains powder of ammonium iron 3 hydroxide. Nope. So first, he will drop in some citric acid. 1 drop. And just pour it all in. So the citric acid is reacting, but it isn't showing much of a difference, right? So we'll need a little more citric acid.
Some is blue. Now it's blue.
I accidentally polluted the citric acid with blue.
Boom.
Now, let's do a little bit of stirring.
It's kind of like a green.
I'm gonna have to get the stop.
Drop, drop, drop.
No.
Oh, now.
Okay.
Here you go.
Oh, thanks. So if I get this, now some of the precipitate is gone. That's because the citric acid actually corroded something away. Although I didn't really prepare that much citric acid. Nope. Now, if I actually filter this thing, I'm actually going to get pure iron sulfate solution, and then the copper will also be extracted. Now, let's move on to the explanation. Hey, stop it. This is not for drinking.
Oh, okay.
Also, whenever you're doing precipitation experiments, do not eat or drink. It might contaminate the food.
Hey.
Now, let's see why the precipitation reaction occurs. Believe it or not, it's actually all about redox reactions. In other words, one thing gets oxidized and one thing gets reduced. Here, let's just have an imaginary beaker with cupric chloride. In other words, copper to chloride. Now copper, this 2 sign means that copper is in its 2+ oxidation state. So there are copper 2+ ions floating around. So in this blue cupric chloride solution, there would be copper 2+ ions, but also 2 chloride ions. Now, also the reactivity series comes here. More reactive metals like potassium and sodium will most likely go into a solution, while the unreactive metals like gold and platinum would start to precipitate. Now, if you look at the reactivity series, you will go potassium, sodium, magnesium, aluminum, manganese, zinc, iron, tin. So tin is more reactive than copper. In other words, tin will venture out into the solution in the form of tin 2 plus ions. So in other words, which means it's a redox reaction. So tin's oxidation is tin atom into tin 2 plus ion and 2 electrons, while copper's reduction would be copper 2 plus and 2 electrons becoming copper metal. In other words, a long time later, the beaker will have colorless tin chloride and copper metal precipitation. But remember when I mixed ammonium iron 3 sulfate? Now that involves another factor. Ammonium iron 3 sulfate involved acid strength. So per chloric acid, hydrogen iodide, hydrogen bromide, hydrogen chloride, nitric acid, sulfuric acid, phosphoric acid, hydrofluoric acid, carbonic acid, acetic acid, and then water. Now here I wrote all the conjugate bases of the acids. So perchlorate, iodide, bromide, chloride, nitrate, hydrogen sulfate, dihydrogen phosphate, fluoride, bicarbonate, acetate, hydroxide. Then there's sulfate, hydrogen phosphate, carbonate, oxide. And then the ones with the 3 minus charge would be phosphate. So here I have ammonium iron 3 sulfate. Now sulfuric acid, or sulfate, to be exact. Sulfate is a stronger acid, so it will remain in the solution. But if this was not a complex of H2O and did not involve it, then the precipitate would actually involve ammonium carbonate, iron carbonate. But because it's a complex of water, here water is actually a weaker acid than carbonic acid. In other words, it will react and then go out of the solution. And so that's why it's iron 3 hydroxide, featuring iron in its 3 plus state, which it used to be in its normal compound. Now let's see two examples of precipitation. So let's say I have gold chloride solution in this test tube, or should I say gold 3 chloride. And then if I drop a little bit of aluminum phosphate, the gold is less reactive than aluminum, so it'll come out as precipitate. So it should be something inside the precipitate. But not only that, we also have the acids. Chloride is the conjugate base of a stronger acid than phosphate's conjugate acid. So the chloride will remain in the solution, but the phosphate will precipitate out of it. Also, then there's the aluminum and the 3 chlorines. So there's solid gold phosphate and aluminum chloride in an aqueous solution. How about another one? Here I have a beaker, and let's get something fancy. Say a flask full of lead sulfate. Now, the lead sulfate I'm using would be, let's just make it a lead 2 sulfate. So PbSO4. Which means that the Pb, or lead, will be 2 plus, and the sulfate, which is obviously a 2 minus. Now, what if I just decide, just for fun, drop a few iron nails and a piece of aluminum foil? Which one will most likely react with the lead sulfate? The iron nail or aluminum foil crumb? Pause the video and think about it. Now, if we go back to the reactivity series, the lead is both less reactive than iron and aluminum. But aluminum is more reactive than iron. So the aluminum will get seeped into the solution, becoming aluminum sulfate, which looks like this in its chemical formula. It's actually kind of complex. How about another example? Say, here, let's get another flask. This time, I'll put in some, let's see, aluminum chloride. In other words, there'd be aluminum 3 plus ions and chloride N ions. So chloride. Next, I decide to drop in an iron paper clip, or just a few of them, and then I put in a sheet of magnesium. Now, which one will react? Well, if I didn't put in the magnesium shaving, nothing would actually happen. That's because iron is less reactive than aluminum, so therefore iron would just stay in its metallic form and aluminum in its ionized form. That is, as long we need it, because this thing's in an aqueous solution, the iron would possibly rust if I just put it in there for too long. But what if I get the magnesium shaving in? Well, then the magnesium will react and then emit magnesium ions. And then the aluminum would precipitate onto the magnesium. So, like that, magnesium's oxidation would be magnesium 2 plus and 2E minus, while the aluminum's reduction, and let me change the coefficients a little bit. 6E minus equals 2Al, or aluminum metal. So I actually got the paper clips out of there, and then I have some magnesium chloride solution. Magnesium ions and chloride ions. But say, what if I dropped a bar of calcium? Now, we can actually go on and on until we hit the most reactive metals. Well, there are actually more reactive metals than potassium, but let's just end with potassium for today. So, in other words, precipitation is when a less reactive metal and the conjugate base of a weaker acid gets kicked out of the solution and becomes a solid. Say, the gold phosphate example we had. It will have a cloud of gold phosphate inside of a clear, colorless solution of aluminum chloride. I don't actually know the color of gold phosphate, so I actually just put an orange. But anyway. So, well, this was our video of precipitation. Thanks for watching, and see you in another video. Bye!